Well, hi everybody. We're going to have a very exciting journey today into the land of conditional probability, and specifically we're going to look at Markov chains. Woo! This is about conditional probability, where the probability is conditional only upon the immediately preceding event, okay, and nothing else. The immediately preceding event, and you'll see what I mean when we get into this. All right. Okay, let's get going. We've got Big Pete. Big Pete is a fitness enthusiast who likes to combine commuting to work with his exercise. He rides his bicycle to work on some days, whilst on other days he drives his car to work. If he rides his bike to work on a particular day, then the probability that he will ride his bike on the following day is 0.4, because poor old Big Pete gets a bit tired. However, if he drives his car to work on a particular day, then the probability that he'll ride his bike the next day is 0.8, because he's all nice and rested and pretty keen. So, on Monday, there's a 50% chance, depending on how he feels when he wakes up, that Big Pete will ride to work. So, what is the probability that he will ride on Tuesday? That's part A. Part B asks us what is the probability that he'll take his car on Wednesday, and part C says what is the probability that he'll ride to work on Friday. Now guys, we've been used to doing all this stuff with tree diagrams. However, let me assure you that the tree diagram is going to become a forest diagram once you get from Monday to Friday. So the tree diagrams, whilst they're very visual and very useful for one or two transitions from the initial position, they get to be rather twiggy and Amazon jungle-like after a while, so we don't want that, do we? No. So let's just, I'm trying to convince you to have a look at the Markov chains, which are full of matrices. Yes, I know. Just put your jaw back up to its proper position. Don't worry, matrices will become your friend rather than your enemy after we finish with this. Okay, part A. Right, now, we're going to represent this with a tree diagram because that's what we're used to doing. So there's Monday. Big Pete has a 50% chance of riding or taking the car. That's day 1. And day 2, that's riding on day 2 given that he rode on day 1. We've got car 2 given that he rode on day 1, and then we've got riding on day 2 given that he took the car on day 1, and car 2 given that he took the car on day 1. Now we can write those probabilities in. Yes, that's day 2. 0.4 is what we were told, and that one there must be 0.6 because they've got to add up to 1. After all, he either rides or he takes the car. There is no other possibility, so that has to add up to a probability of total of 1. All right? And the other ones were 0.8. If he took the car the first day he wants to ride, so he's 0.8 probable that he'll ride, and then 0.2 that he'll take the car again. Okay? All right. Now, let's just see what we've got. We can easily work this out now because the probability that he'll ride on Tuesday, there are 2 riding events there on Tuesday which we can add their probabilities up. The first one is a compound event of 0.5 and 0.4. And the second one is a compound event of 0.5 and 0.8. So that's easy to work out now. We've got a half of 0.4 is 0.2, and a half of 0.8 is 0.4, which gives us a total probability of 0.6, Mr. Box. Great! Okay, nice little tree diagram exercise. No problem. But now you need a chill pill from now on, guys, because I'm going to get into all the gobbledygook of what this all means. Now, let me show you. There's the first one I've got there. So I'm saying to you that the very first twig of that tree diagram is the probability of R2 and R1, isn't it? Yeah, we rode on both days. So it's the probability of, according to the multiplication formula, it's the probability of R2 given R1, because it's definitely given R1, because that tree diagram indicates that we definitely rode on day 1 for that particular twig. Good, times the probability of R1. Yeah, and that's it. Okay, so there's the probabilities, and we multiply them together and we get 0.2. Now the other one, the third item there in that third twig in our tree diagram, we get that. That's the other riding event. That's the probability of riding on day 2 given that he took the car on day 1. Okay. Now you see if you can work out that what that formula is going to be on the right hand of the equal sign. Come on, before I do it. Can you see? Okay. Yes, I think you've got it. So it's R2 given C1, yes, times C1. Good. Now let's fill in the numbers, and we get that, 0.4. Good, and that confirms what we got above in the red writing there, a few lines above, of a total of 0.6 for the riding. Now we're going to do the car bit. Okay, so it's car 2 given riding on day 1, and here it comes. There's the formula. That gets us 0.3, and the last but not least is car 2 and car 1. Okay, so that's car 2 given car 1 times car 1, isn't it? Very good, it is. Now that gets us that, which gets us that. Now hopefully they'll all add up to 1. Oh, they do. Excellent. You always want to check that, guys. Now, super chill pill needed here, because I'm going to summarise how you get to the probability of R2. Remember, there were 2 events for R2. The first and the third entries, they're the 2 black entries on the tree diagram. I'm going to write it all out in full, okay? Here we go, that one and that one, right? Here we go. Yes, and that is, on to the right of those equal signs, we would get this above. Oh, goodness gracious. All right, that's the probability of R2, isn't it? Now, under that, we're going to do the probability of C2. Same thing. It's getting very, very scary. Okay? All right, here we go. That's C2 and R1. That's that one, plus the probability of C2 and C1, which is that one. Okay, let's write it out in full. Ooh. Plus that one. Yeah? Okay. All right, now, you ready? Then we're going to go over the page and we're going to work with that now. Okay? Whoa, there it is. Okay, now that's where we got to, guys. Now, what I'm going to do is I'm going to write out the equivalent matrix expression for that purple line and the green line. And hopefully that'll convince you that we're getting into the land of the forest here, not the tree diagram. We want to simplify things so we can do a transition from Monday to Friday without having to end up with the Amazon jungle. Okay, so here we go. Probability of R2 and C2, notice I've written them as a matrix, right? Equals. Now here it comes. That first matrix to the right of that equal sign is called a transition matrix, okay? It's so named because it gets us it is the key to enable us to transition from one day to the next day in terms of our probabilities. That's why it's called that. Anyway, we're going to, you see how I've written that R2, C2, that column on the left of it, and then R1, C1 across the top. That's very important because it's like a street directory thing, okay? Where those rows and columns intersect, that's what happens inside the matrix. And I want you to do that so you won't get it all messed up when you do these things. There it is. You see what I'm doing? I'm doing a street directory, okay? Row, column, row, column, row, column, row, column, okay? Now, we can fill in the numbers in a minute, but what I'm saying is that the probability of R2, now, do you remember how to multiply matrices? Alright, now you follow me, you look at the purple line above while I read out the multiplication of this matrix, right? I'm saying that the probability of R2, okay, you're looking at the purple line, equals, now I'm going to multiply these matrices, that is the probability of R2 given R1 times the probability of R1 plus the probability of R2 given C1 times the probability of C1. Okay? Now, I'll read off the green line now, and you look at the second line of that matrix below, okay? Starting off with the probability of C2. All right, you ready? I'll read off the green line. You see whether you agree with me from the matrix side of it, okay? So the green line says the probability of C2 is equal to the probability of C2 given R1 times the probability of R1 plus the probability of C2 given C1 times the probability of C1. Now, did you get that? Come on, you've got to admit that's pretty good. And we have condensed that sausage machine that you can see in purple and green above into a very, very concise statement, which you have to agree that's pretty good. Yeah, it is. Now, I scaffold this. I put plenty of little helpers around these matrices to help me. That R2C2 black writing in that column on the left-hand side of that transition matrix, I put like the words the now or today or something like that, okay, depending on the context of the question. And on the top, that row along the top, that's the given bit. That's the yesterday's event or the previous event, okay? So that's what it is. The 2 is the now, subscript 2 is the now, subscript 1 is the then or the given, okay? That's really important that you get that, okay? And there's no problem with you writing that out when you're formulating this transition matrix. So what am I saying? We'll put the numbers in now. I'm saying that the probability of R2 and C2 is equal to, there they go. Now R2 given R1, if you look at the tree diagram above, I'll circle it. It's 0.4, yeah? Okay, now we're going to do the C2 given R1. That's the bottom left item in the transition matrix. Now look at the tree diagram. 0.6, and that's circled 0.6. You see how it works? And those columns add up to 1. Of course they do. They have to add up to 1 because they belong to the twigs in the tree diagram which have to add up to 1. Yep. Okay, now we're going to go top right. It's 0.8 and look at the tree diagram. And of course bottom right is going to be 0.2, which corresponds to that item in the tree diagram. Do you get it? So there's a very close correlation here, guys, between your tree diagram and your transition matrix. All right? You don't have to draw a tree diagram every time you want to make up a transition matrix because you get used to doing them as I've written it in the line above with the street directory kind of approach and the words that help you. You know, the now and the given, or the now or the then, or today and yesterday, or whatever. Okay? Okay, and that's there's the probability of R1, which was 50%, and the probability of C1, which is 50%. Now, guys, that's called the transition matrix, and usually it's given a capital T, okay, which provides the transition from one day or one state to the next, okay? So we can work this out now. The probability of writing on day 2, I'll prove to you that it works the same as what we got on the previous screen. That's going to be, now multiplying the matrices together, okay, 0.4 times 0.5, look at the little matrices above, I've circled them, okay, 0.4 times 0.5 plus 0.8 times 0.5, here they go, there, right? And that'll come to, hopefully, yes it does, you beauty, 0.6. Mr. Box, thank you Mr. Box. Okay, are you starting to get it? Alright, now come on, here's another leap of amazing logic. Here we go, watch this. Now we can say that the probability of R2 and C2 is T, transition matrix, times the probability of R1 and C1, can't we? That's Tuesday coming from Monday, right? Good. Now, but we can also say the probability of on Wednesday, that's day 3 of riding and going in the car, would be the transition matrix times the situation on day 2. But hang on a second, day 2 in the line above has been expressed in terms of day 1. So let us substitute the day 2 situation from the line above in terms of the day 1 situation. What do we get? We get that. We get that. In other words, we've got T squared times the probability of riding and taking the car on day 1. So are you getting this? If you have 2 transitions, it's T squared, or to the power 2, times the probability of the initial state matrix. Okay, if you had 5 transitions, it would be T to the 5 times the probability of the initial state, etc. Yes, etc. Right. The plot thickens. Now we're going to go over the page now on a nice clean screen, and we're going to work out part B using the matrix method. The probability that he will take his car on Wednesday, right? So we're going to revert now to the more traditional type of terminology. The initial state matrix is usually given a subscript as 0, like a ground 0, okay? So that it's more easy to see how many transitions you've got, because then the subscript of whatever you want will be the same as the number of transitions. I'll show you. So like if you wanted to go for Wednesday, from Monday, well Monday is like day 0, therefore Wednesday is day 2, and there are 2 transitions. Do you know what I mean? Hopefully. After n transitions, what are we saying? Then the probability of R sub n and C sub n would be T to the n times the initial state matrix, yes? Good. So therefore, and rewriting it out even in more general form, I've reduced the initial state matrix just to S, capital S, sub 0, okay? State 0, ground 0, guys. Okay. Now, therefore, looking at Wednesday, that's 2 transitions from Monday, isn't it? Therefore, we can easily work it out now without the tree diagram. It comes to that. Wow! Look at that. Okay, now if you get your trusty calculator out and work that out, there it is. I have done it for you. And you can see I've stored... I've done it all. There's just one line that scrolled up so you can't see it. But I have done the whole thing for you. I put in that the transition matrix was whatever we said it was. And I put in the initial state matrix as S. And therefore I did T squared times S. And what did I get? That's car on Wednesday. Big Pete's got a 0.44 probability of driving his car on Wednesday. Okay, there you go. Do you like it? Therefore, we're looking at 0.44, Mr. Box, thank you. Okay, how do you like that? Now we're going to do the Friday thing, I think. Yes, Friday. Now, how many transitions is it from Monday to Friday, guys? 4. Of course it is. Tuesday, Wednesday, Thursday, Friday. So therefore, let's work that out, how easy it is now with our trusty calculator. Now, I haven't actually given you a screen dump of this, but it's really easy. It's, what is it? You get that. You get that. You just T to the 4 times the initial state matrix, and you get that, which is now which one do we want? We want the riding to work on Friday, which is the first one, the R1. Yeah, it's that one. So therefore, the probability that he's going to ride on Friday is 0.5696. There you go. There's Mr. Box. Thank you, Mr. Box. Do you get the picture? I think you are. Now, a little bit of a summary of what Markov chains are characterized by. First of all, we have a transition matrix T, capital T, which is a square matrix denoting conditional probabilities where the probability of a successive event is dependent only on the immediately preceding event. All right? Yes. And the second one, initial state matrix S sub 0, which has only one column, not a square matrix, and which gives information about the beginning, the initial state of the sequence of events, yeah? And thirdly, we have the elements of the initial state matrix may be probabilities. Yes, they may be probabilities, which we're used to, but they can also be percentages, guys. And shock horror, they can just be, with Markov chains, they can just be ordinary old numbers. Good heavens, I know you're very shocked, but that's it. That's it. That's the cold, stark facts of the situation. Markov chains are amazing things. So, how do you feel? All right, I'm rabbiting on here, so let's get going onto a different situation. We've got Hertz Car Rental Company has branches in Melbourne and Sydney. Cars are usually rented for 3 days and then returned to the same place. However, wouldn't you know it, some people don't do that, and the probability that a car rented in Melbourne will be returned to Sydney is known to be 0.3, and the probability that a car rented in Sydney will be returned to Melbourne is 0.15. Okay? That's interesting, isn't it? That's very interesting. So I would say that means you're going to get cars more gravitating towards Sydney, wouldn't you? I think so, because the probability of them being I don't know. No, don't worry about all that. I'm going mad here. We'll just do the sums. At the beginning of the month, Hertz has 120 cars in Melbourne and 159 in Sydney. Find the following. A, the transition matrix T, which can be used to represent this information, and B, the estimated number of cars in each city at the end of 6 weeks. We can do this. No problem. We can do this. So, the question is, look, you've got a whole lot of words there. How how can we characterise this mathematically? How can we get the words into the maths? This is usually the problem for the poor old student, okay? You've got to think about this and do a lot of them so you get better at it, okay? All right, now we've got returned locations given the hired location. That's what I really think we're talking about here. The final location where the car resides after the end of the hiring, given where it was hired from. Wouldn't you think that's what we're on about here? I think so. So, we're basically interested in where the vehicle is returned to, given where it was hired from. Just to say it again in a slightly different way. Okay. So, let's say we've got the now I'm going to talk about Melbourne and not Melbourne because that's what I'm more used to with probabilities. You know, we could have said just Melbourne and Sydney, but you know, I feel more comfortable with Melbourne and not Melbourne. Do you agree with that? All right. That's the final destination. Yeah, and that will equal my transition matrix. Now you notice I've written down there on the left hand side, I've written end location, and then the top that top row in red is the given the starting location. All right. So if I write that out, Melbourne not Melbourne, and Melbourne not Melbourne. Okay. Now we can do our street directory. Melbourne given Melbourne, not Melbourne given Melbourne. Melbourne given not Melbourne, heavens, you start to go stir crazy after all this after a while. Not Melbourne given not Melbourne, all right? Now, then that's times our initial state matrix, which was 120 cars in Melbourne and 159 in Sydney. Now, guys, we're nearly there. We've just got to put in the numbers now. Okay, now, what was the Melbourne thing? Goodness. 0.3. Now, what does it say there? That's a car rented in Melbourne being returned to Sydney. That means not Melbourne given Melbourne. Do you agree with that? Okay, I'll say it again. A car rented in Melbourne, returned to Sydney. So that means it's returned to not Melbourne, given that it came from Melbourne. Okay? Now, where's that one? It's there. Okay? It's there. Okay? Therefore, the other one in that column must add up to 0.7. Okay, what's the other bit of information we got here? Car rented in Sydney will be returned to Melbourne. So what's that mean? That Melbourne, what is it? Rented in Sydney. So that was that's Melbourne given not Melbourne. Is that right? Melbourne given not Melbourne. Yeah, that's 0.15. So that goes there. Okay, you getting the idea of all this? Therefore, the last item in that column must be 0.85. Okay, guys, we've got it. That's our transition matrix. Okay. And that's times the initial state thingy. Yes? All right, now, therefore, we can say that our transition matrix is that thing. Now, look, guys, if you happen to be a Sydney-sider and you like to sort of have Sydney in the thing, you could have done it slightly differently than what I did it, and you might have ended up like that. Sydney, or not Melbourne and Melbourne, in that order, and you might have ended up with that transition matrix. Look, it matters not. Really, depending as long as you're consistent with what you're doing, it's fine. It's just fine. Okay, good. Now B for you and me, the estimated number of cars in each city at the end of 6 weeks. Okay, 6 weeks means did you remember in the question they said they hired them for 3 days? Well, 6 sevens are 42 days divided by 3 day stints is 14 transitions. Okay, so we've got to work out the situation after 14 transitions. So therefore, what I'm saying is that the probability of Melbourne after 14 transitions or not Melbourne after 14 transitions is t to the 14 times the initial state matrix, which gets us, and there it is, guys. I've done it all for you. There we go. I've put the transition matrix in as t. I've put the initial state matrix as s, and I've gone t to the 14 times s, and I've got that thing. Now, what are we supposed to be finding out? Oh, the estimated number of cars in each city. All right, well, that means, look, we've got 93.0063 for Melbourne and 185.994 for Sydney. Well, obviously you can't have 93.0063. You can't have 93.0063 cars. So you do it to the nearest car, just to make it sense, yeah? So that's Melbourne. That's got to be Sydney. So our answer is the estimated number of cars in Melbourne's 93 and 186 in Sydney, and that's to the nearest car, okay? Hurrah to the nearest car, And Mr. Box, I think, there he is. Thanks, Mr. Box. That's our answer, guys. And wow, that was pretty exciting. An exciting journey, and you're a star, and in fact, you're even a bigger star. Yes, you are, and you'll go far. So, hurrah! We finished transition matrices, and you can go and have a cup of tea, and I will too. Thank you for listening to this little presentation, and we'll see you next time. Bye!